It's probably going to be part 2 now. Read the information below. No thanks. I'm going to have a look at the questions first. So, atoms of all these isotopes have the same number of protons in their nuclei. Let's have a look. Same number of protons. Well, that is just, if you tick that box, then you're not looking at this. So, all isotopes have the same number of protons. Proton number, okay, incorrect. An atom of uranium has 92 neutrons in its nucleus. Well, the nucleon number is just the mass number. To get the number of neutrons, you take away the small one. Take the small one from the big one. So I've done that there. 238 minus 92 equals 146. So it hasn't got 92 neutrons. It's got 146 neutrons. An atom of californium has the greatest number of protons. Well, there's californium, and it's definitely got the greatest number of protons. So I've ticked that. An atom of californium has the smallest number of neutrons in its nucleus. Well, let's have a look. 238, the big number, take away 98 is going to be 140. And that makes sense because I'm going to have the smallest number of neutrons because all these have got the same mass numbers. So if you're taking away less, you're going to have more neutrons. So 238 minus 95, the outcome is going to be bigger than 238 minus 98. So that's going to have the least number. Uranium is not a naturally occurring element. I'll come back to this one. And then an atom of uranium has 92 protons in its nucleus. That's easy because uranium, 92. So that was an easy tick there. Now let's talk about uranium is not a naturally occurring element. Well, it says in this statement here, the first 92 elements in the periodic table occur naturally. So uranium is part of the first 92, look. 92 is the 92 second element in the periodic table. So uranium is not a naturally occurring element is incorrect because it is. Because it says there the first 92 elements occur naturally. Complete the equations. So I like these because they throw a lot of students off, but they're quite easy. This arrow, think of it as an equal sign, 238. So each number, think of these now as separate. 238 equals 4 plus something. So 4 plus something equals 238. So 238 minus 4, you could think of it, 234. 234 plus 4 gives us 238. The same here. 2 plus something is going to give us 92. 2 plus 90 is going to give us 92. Or you could think of it as 92 minus 2 gives us 90. It's up to you. Circle the 2 correct isotopes. Now, an isotope is the same number of protons, but a different number of neutrons for the same elements. You can see they've got the same element, U, but only 2 of these are real because uranium's got 92, a proton number of 92. If it was 91, it would be something else. If it was 93, it'd be something else. So this is not actually uranium. This is not actually uranium. 89 would be something else. But you can have different big numbers. I shouldn't say top numbers because sometimes they're at the bottom. But these mass numbers, remember, a radioactive isotope is, there's an imbalance between the number of protons and neutrons. So it's the one with the same small number. Nearly there. The diagram shows 3 types of nuclear radiations. So, it just wants you to use these words and fill in the blanks. So, if that's paper, this has got to be aluminium, and this has got to be lead. We got to get that from our learning. I mean, it's always paper, aluminium, lead. Sometimes you get paper this end and lead this end. So they've tried to do it backwards to confuse you. So I've used aluminium there, lead there, and then beta is stopped by aluminium. It's quite a thick aluminium, and gamma is stopped. Well, you can see it's actually going through some lead there because it's got to be thick lead or concrete. And then alpha is getting stopped by paper. State why the readings are different on these measurements. So you've got someone taking the activity, and they've wanted to take a mean there. Why are they different? Because it's a random process. You cannot predict radioactive decay. You can predict it over time, and you can predict it with a lot of results. But at any one result, you can't predict because it's such a random process. Calculate the mean activity. Well, 20 plus 22 plus 18 plus 19 plus 21 there. Over the amount of results, 1, 2, 3, 4, 5 results. Is going to give you the answer to the next bit, which is 20 counts per second. And then name one natural source of background radiation. You pick radon from rocks. You can find it in food, cosmic background radiation. You can even find it in animals, okay, for 1 mark there. 2 more questions, or 2 more pages. Complete the following diagram to show the count rate in terms and the time shown. So it starts at 800 counts per minute. Yeah, that's at the start. So 1 half-life is going to half the activity. Remember, half-life is the amount of time it takes for the activity half, or the mass to half. In this case, it's the activity. So it goes from 800 to 400 to 200 for 2 marks. Easy marks. That's just showing. This is more for the triple question then. I think there was a question which I skipped. So we're going to go straight to the last question now. A student correctly draws diagrams of helium atom and an alpha particle. We can see the helium atom has got 2 electrons there buzzing around, but this alpha particle hasn't got any electrons. That's why we say it's a helium nucleus. So similarities, they both have 2 protons and they both have 2 neutrons, don't they? 2 protons, 2 neutrons. But the big difference is this one has no electrons. And then we've got one of these nuclear equations. I love these because it's easy maths. 210 equals 4 plus something. So 206 plus 4 gives us 210. 2 plus 82 gives us 84. Again, any questions on this, come and see me. Very important. Easy marks. These, what was that, 2 marks? Yeah, 2 marks for that. So we can't be avoiding that one. State why the isotope of polonium is radioactive. Whenever something is radioactive, if it's asking you why something's radioactive, there's an imbalance between the number of protons and neutrons. We said it earlier. We're going to say it again. Explain why in 2006 this Russian guy died within weeks of swallowing some polonium-210. Well, the big clue there is alpha decay. If you're putting that inside you, then you're in trouble because it's very, very ionizing. And it's going to mutate that cell to the point where you're not going to live very long. And that is that paper done and dusted in 20 minutes.